So good morning, everybody. I am really happy and humbled to see all of you here for the defense, and I hope you have a fun and interesting time. Humans have always been fascinated by autonomous vehicles. When I was preparing for this defense, I tried to see if I could trace back in history just how far back the first reference to autonomous vehicles could be found. And the answer was rather surprising. What you see here is a sculpture on the wall of a temple showing a scene from Hindu mythology where a demon king is flying through the air in an autonomous vehicle called the Pushpak Viman. This was created by a fine fellow named Vishwakarma, who is considered in mythology to be the principal architect of the universe. And the demon king stole this from him and led an interesting life. But moving forward and westwards, in 130 BC, King Phratus II of Parthia was supposed to have gone into battle on a magic flying carpet. So moving ahead from mythology, if we come into the Renaissance age, Leonardo da Vinci made some plans for a clockwork car which could follow a predetermined path. And someone actually made this. So if you look for a video on YouTube, you'll find a wooden cart that is going in a certain way. The first autopilot for aircraft was invented barely 10 years after the first flight in 1903. What you see on the screen in front of you is called a mechanical mic. And this autopilot was instrumental in the first flight around the world in 1933. In 1920, the Lindrikar Wonder was the first car that was operated driverlessly on the streets of New York. There was a car behind that was controlling the car using radio control. People as early as 1935 were already imagining what it would be like to have a future where humans did not drive any cars. And in this book, The Living Machine, people are talking about how the blind people would be safe and how parents could send their kids to school in driverless vehicles. This, in 1950s, is the vision of what a driverless car could look like. You see a family playing some game, and this was the electricity companies that were actually promoting this kind of vision. The Stanford cart in the 1964s, this was actually the first vehicle which could autonomously find a path among obstacles, and it famously didn't find an obstacle by the side of a road and it just went off and went into a ditch. But we've come hopefully some ways since then. Quiz question. Do you know what the biggest project in autonomous driving ever was? It was the Eureka project Prometheus, 749 million euro, running from 1987 to 1995. And Professor Dick Ernstmann from a university in Munich famously used a lot of Mercedes-Benz vehicles, and he was able to achieve quite spectacular speeds when he was driving from Munich to Odense in Copenhagen, no, in Denmark, and back. He actually reached speeds of 180 kilometers per hour completely autonomously. So this was effectively the history, and after this project, everybody and their brother jumped onto the bandwagon. You had the DARPA challenges, and you had Google, and now every major automaker worth their salt is working on autonomous driving. In fact, the excitement has reached such a fever pitch today that this is the Gartner Hype Curve for 2015. And what I just wanted to show, right here at the very top, autonomous vehicles exist. So it is interesting to see this development of autonomous vehicles through history. And at every single point, people have been saying, this is it. This time, it's going to work. And so it is with a long and rich heritage that I stand before you today to say, autonomous driving, this time, it's going to work. So there are reasons to think why this is the case, and that has to do with better sensors, maturation of embedded systems, a better theoretical understanding of the problem, and a few other things. We can get into it during the discussion. But this is also a slightly cautious note to say that a few tough problems still remain. And in this thesis, we will look at how the state of the art has been advanced to a little extent. What we'll do is we will look at the modern context of autonomous driving and then delimit the discussion to the focus of this thesis and see what kind of research methods were used. We will then very quickly go through some of the key highlights of the research. It's always tough to cover 6 years of research in a 30-minute presentation, but hopefully we can do a deep dive into the technical topics during the discussion. And then we'll wrap up by looking at the impact that this thesis has had on the research field. So the modern context is really not about autonomous driving per se. It's never been about one vehicle operating in isolation. The concept is of intelligent transport systems wherein every kind of vehicle, be it trains, be it cars, be it boats, be it airplanes, are all constantly connected to the grid and talking with each other. Can you have, for example, a system where 100 people are getting off the subway at Techniska Högskolan and the bus operator knows that there's 100 people coming and they want to go and the bus is arriving right on time just as the people exit the subway station? Do you think this is possible? Well, it is. Ericsson seems to think so, and a whole lot of other people in the European community. So applying intelligent transport systems to road vehicles, there is a scenario known as cooperative driving. And what cooperative driving implies is that road vehicles within a certain geographical area are talking to each other and the infrastructure like traffic lights and speed signs so that they can better decide how they can move through the environment. And cooperative driving doesn't necessarily have to be autonomous. You can have a human at the wheel of your vehicle and still get information about other vehicles to make better decisions. And then you have autonomous driving, wherein a vehicle does not really depend on other systems. It has enough perception sensors so that it can decide the state of the world around it and go from its current location to its destination without crashing into obstacles or pedestrians. And of course, you can have an autonomous vehicle that talks with other vehicles to have a scenario for autonomous cooperative driving. A quick thing on terminology. Autonomous driving has been referred to by many different names. You can see some of them up here. And each name has a certain nuance. So there is some distinction. But for the purpose of this talk, for the next 2 hours, we will refer to it as automated driving. And the reason we do that is because last year SAE published the J3016 standard and they choose the word automated driving and now that becomes the standard. So that is what we will use. We will also use the term autonomous driving interchangeably with automated because when this research started, the SAE 3016 standard was not yet released. So autonomous, automated, slightly similar. There are, of course, degrees of automated driving. And what you see in the first row here is something that goes from driver only to full automation. And these degrees of autonomous driving were first specified by NHTSA for vehicles in particular, because in general, there have been autonomy levels in many different domains for a very long time. So NHTSA classified level 0 for driver only and level 4 for full automation. And then SAE came along, and I just have a suspicion that for standards, it's very important to be similar but slightly different. So what they did is they have the same levels, but it goes from 0 to 5 instead of 0 to 4. And in this thesis, we will talk about high automation and full automation, which is levels 4 and 5 from SAE and level 4 from NHTSA. So why automated vehicles? There's a bunch of reasons. I would just like to draw your attention to one statistic from last year. This was made by NHTSA, and NHTSA incidentally is the National Highway Traffic Safety Association from the United States. And take a look at this row here. What it says is that a staggering 94% of accidents in road vehicles can be attributed to human factors. So if we introduce autonomous driving, we have the potential, not the guarantee, but the potential to bring this number down from 94 to 0%. Why cooperative driving? A number of tests and simulations have been carried out. Netherlands especially is leading this with the GCDC competitions and other convoying happening. It's mostly driven by TNO in the Netherlands, and the California Path program in the US have also been working on cooperative driving. And what they see is that today the number of vehicles in a lane per hour is about 2,100 in many metropolitan areas. And with cooperative driving, there is the potential to more than double this. Similarly, there are benefits for emissions, fuel, and increased speeds. So in summary, we want to go in for autonomous driving and cooperative driving for reasons of safety, for having a better impact on the environment and the economy, to better utilize our infrastructure, and most importantly, to better utilize our time. It's like if you spend 40 minutes a day commuting, that is a loss of quality time. My friend Victor, sitting here, once told me that if you move that 40 minutes to the end of your life, that commute has essentially killed you 40 minutes earlier. And now I live in Silicon Valley, and in 30 days, I spent 40 hours in my car commuting. That's one full working week in a month. So if we jump right in and if we ask ourselves, how do we make an autonomous car? What are the main components? You can see some of the main components here. You will have some kind of sensing, some kind of localization to tell you where you are, and then you will generate a trajectory among obstacles that will take you to your goal. And this trajectory you then feed to a vehicle platform which will hopefully realize that trajectory. And it's very easy to think that today we have fairly sophisticated cars. What if we just replace the human being by a really smart computer? Is that actually all it takes? Many people who get into autonomous driving seem to think so. And then if you spend any time at all in this field, you realize that this is a rather simplistic approach. It doesn't actually work because you need to co-design the vehicle platform with the specific artificial intelligence that is driving the platform, and there are many tight threads of integration. So a more structured approach is necessary, and in this thesis, we've been looking at one such structured approach. We will zoom in on pictures like this. You won't see the details of all these pictures, and that's okay. We will zoom in on it at the time as the time comes. But the thesis has focused mostly on architecture, and architecture is one of the 4 big areas that contribute to autonomous driving. Others being algorithms, systems engineering, and there are a lot of social and regulatory concerns. So if you zoom in on the architecture part, there's a lot of different kinds of architecture. And in this work, we've actually built quite a few autonomous vehicles. So we've covered all the different kinds of architecture. But the main contribution of this thesis has been in the area of functional architecture. Those are the main scientific contributions. And the reason why we focus on functional architectures is that these architectures tell the broad patterns and the logical view of the system without getting bogged down by a specific implementation technology. So they often serve as reference solutions for problems of a certain class, and hence a superset of functional architectures is often called a reference architecture. And the main scientific contributions of this thesis are 2 reference architectures, one for cooperative driving and one for autonomous driving. So the hypothesis underlying this research work has basically been that a reference architecture for highly automated driving exists. Not just any kind of reference architecture, but that which is general enough to be repeatedly instantiated to provide a sufficient solution in a variety of automated driving solutions. And I really want to emphasize that this is a work of engineering and the job of an engineer is to provide a sufficient solution to a problem. So, of course, the research question that follows then is, what is a suitable reference architecture for autonomous driving? And this question is quite broad. It's split into a bunch of different questions. We won't go into all of them today, but they are there in the book that you have in front of you. What was the research method used? One very important thing was to keep the research real. So it is grounded in multiple autonomous driving projects, 4 of them in fact, where we had actual vehicles, both vehicles that are commercially on the streets as well as novel prototypes being driven autonomously. And when you say that an engineer generates a sufficient solution to a need, then the task of engineering design is to identify what constitutes a sufficient solution. And if you do a lot of practical prototypes, can you generalize from that experience to create knowledge that is repeatable, reproducible, and so on? And then we complement this very emphasis on prototyping with state-of-the-art surveys and expert interactions with people not only from the automotive domain, but from other domains like aviation, industrial automation, medical, because this is a safety critical system. And prototyping. What we did was, there were 4 large projects, and we'll briefly talk about them: the Grand Cooperative Driving Challenge, the COACT project, and a few others. And these were complemented by research projects, 3 of them, throughout the past 6 years. And in these projects, we had a number of different project partners that you can see. So this research is not conducted in isolation, especially when it comes to autonomous driving. It is almost impossible now for any one person to cover the broad spectrum of technologies needed in order to generate a truly autonomous vehicle. So this is just a quick view of what the Grand Cooperative Driving Challenge looked like. There was a lead vehicle that was driven manually, and then all the other vehicles followed this lead vehicle autonomously. And the lead vehicle would speed up and it would slow down, and the vehicles behind would follow in a relatively good way, so that the string effect that often results in lower traffic utilization throughput is minimized. So here the big truck here in the back, it's the Scania R730 series, which until recently was the biggest commercial truck in the world. Following that, the next year there was a Swedish challenge called COACT, which was very similar to GCDC, but unlike the GCDC, it did not restrict itself to purely longitudinal motion. There was lateral motion also, so you could go into the other lanes, you could overtake vehicles, and so on. Commercial vehicles or vehicles manufactured by big companies come with legacies that often impose very tight constraints on what you can do with them. So there was a vehicle created at KTH called the RCV, Research Concept Vehicle, which is a clean sheet design, completely electric, and it's basically a bunch of motors, a battery, and a computer. So you can drive it any way you want, and there was some effort on making this autonomous, and not only did we show things like autonomous parking on the RCV, but this became the basis of bootstrapping a very nice project in Silicon Valley, where we will be using the RCV to create a completely autonomous vehicle. I can't talk too much about it because of investor concerns, but suffice it to say that this vehicle will not have a steering wheel, it will not have brakes or any kind of pedals, and the human occupants will have no chance at all to take over control. So the main contributions of this thesis are being captured in a set of 13 publications, out of which 11 were peer-reviewed, and we'll go through some of those in the presentation. The contributions can also be classified into different categories. Before you jump into solving problems, you need to understand what is the state of the art. If you talk to practicing engineers, what are the obstacles they face and what are the challenges they think hinder introduction of autonomous functions. And then you have the scientific contributions and engineering reports that document in exhaustive detail how a particular autonomous vehicle was built. And it's important to not just stay at the research level, but to train the coming generation of engineers. And there has been some work done to show also how you can train current students so that they can be better engineers. So the first publication was Architecture Challenges for Intelligent Autonomous Machines. And there was a big workshop conducted at KTH with more than 70 engineers who came from big companies around here, Atlas Copco, Ericsson, Volvo, Scania, and so on. And the main outcomes were that some of the main challenges in constructing autonomous systems today are in creating a valid world model. How does the machine know what environment it operates in and what the characteristics of different objects in that environment are? And similarly, especially when it comes to domains like aviation, how much human needs to be in the loop? Because if you don't let the human being fly very often, then the capabilities of the human degrade. But at the same time, you don't really want the human to fly very often because that job is for the computer. It's a tricky balance. And extra functional properties like safety, redundancy, determinism are more important than ever. Publications B and C talk a lot about platooning and cooperative driving. One of the two principal contributions has been a reference architecture for cooperative driving. Again, I don't expect you to go through each tiny block here. We can do that during the discussions. What I wanted to point out is it centers around a so-called world model, which is like a big central database. You get data from the sensors into the world model, and you've got consumers, and then you've got a bunch of tasks that take data from the world model, process it in some way, and push it back. And an architecture, this is a representation of an architecture, and it's important to understand that the architecture representation is not the same as the architecture itself. Like the map is not the territory, and the way that you can have many different kinds of maps, topographic maps, precipitation maps, physical maps. Similarly, you can have different kinds of architecture representations. They are technically called views that arise from different viewpoints. So there is a view showing what are the main logical functions. There is a view showing how do the different software modules map to the logical functions. What hardware do they run on? How does the different hardware connect to the rest of the hardware in the vehicle, and so on. We have publications D and E on autonomous driving, and the autonomous driving architecture has really evolved from the cooperative driving architecture. So we did an analysis of, we already have an architecture that can drive a big truck autonomously on public streets. What if we take the driver out totally? And that resulted in first asking, what are the different important components in an architecture? And those were split into three categories related to perception, decision and control, and vehicle platform. And then it's important not only to say what the different components are, but how do you distribute them across an architecture? Do you create layers? What are the pros and cons of distributing, say, the decision and control in layer 1 versus layer 2? And there has been some analysis done of that as well. And we have a proposal for a reference architecture that is split into three different layers. And what it tries to do is, it really tries to make things modular so that you can have a vehicle platform and an artificial intelligence layer. And would it then be possible to swap out the vehicle platform with a different vehicle platform? And this is very important to manufacturers because they have typically a number of different cars or trucks, and they want to have a unified architecture for all of this. And it also takes into account the reality of the situation that modern vehicles are already extremely sophisticated, and there are ECUs inside a vehicle to which you can say, this is the desired acceleration or this is the desired velocity, and you're going to get that. So this architecture leverages those kind of features. If you spend any time at all doing practical systems, you quickly realize that having an amazing architecture is not enough. What you need is also a very systematic process for how you design such systems. In fact, if you look at standards for safety critical systems, they don't consider the artifact to be as important as the process. You need to follow certain rules, follow certain steps, generate a big amount of documentation, and there is a joke in the aviation community that when the paperwork weighs more than the airplane itself, then you are good to go, then you have some hope of getting certified. So the thing is, there have been a lot of models for doing systems engineering. You have the V model, which is very, very popular and recommended by ISO 26262, which is the prevailing best practice in the automotive world. But if you go to a startup environment, or if you are prototyping and you try to impose a full-blown V model, it's just not going to work. You will be one lone voice, one architect in the organization saying, guys, architecture, process, and they'll be sitting there and hacking away at their code. It's not going to work. So what you need is really a lightweight process that allows you to be structured and that can scale. Eventually, once you have a proof of concept done, it can scale to something that has some hope of getting certified. And we have such a systems engineering process, which is mentioned in paper E. And it also shows the different levels at which you have to describe the system, the corresponding requirements, test cases, and what are the different kinds of models that you have to make at different levels, like functional architecture, technical architecture, and so on. So, as a systems engineer, your dream is really to have a big dashboard where you have your architecture, you have the requirements, you have the test cases, and they're all linked to each other, and you can click on a test log and say, okay, this was tested on this vehicle with this configuration, which validates these parts of the architecture. So there is some work on systems engineering, and when it comes to implementation, since autonomous vehicles are so immensely complex, you can't actually test everything on a physical vehicle right away. What you want is the ability to mix a virtual vehicle in maybe a synthetic 3D environment, and we have such a setup that we've used with great success repeatedly in our experiments. So for example, you can take a hardware in the loop simulation of a drivetrain and drive it with a real ECU in a synthetic 3D environment. One of the big areas that is actually going to contribute to development of autonomous driving is actually 3D graphics and gaming. In fact, we are using the Unreal 3D engine to create a synthetic environment where you can use technologies like ray tracing to simulate a laser sensor, for example, a bunch of other sensors. So I would just like to take a step back and talk a little bit about something that might sound a bit more philosophical. Certainly not things that a lot of nuts and bolts engineers talk about, and that is the realm of machine consciousness and self-awareness. And an interesting question to be asked is, does an autonomous vehicle actually need to be self-aware? In fact, are you and I self-aware? That becomes too philosophical. But if you look at the fields of neurobiology and computation, it has been shown repeatedly, especially in robotics, that machines which can dynamically create new models of their environment, which can synthesize these models and refine them, are more robust in problem solving and generally adapting to changes in their environment. There have been a number of architectures for these kind of things. They are called cognitive architectures. And we made a survey of the main cognitive architectures and found that although they are very good in what they do, because they have different priorities than architectures for safety critical systems, they actually fall short in a number of ways, like being real time or managing resources critically. They do better at learning, but the predictability of that learning is very bad. So what we follow today really is a system of carefully handcrafted architectures, and that is often called the constructionist paradigm. And there is an argument that we need to move towards a constructivist paradigm, which lets vehicles synthesize models of the world on their own and make a lot of errors and learn from them. So self-organizing complex systems. The problem with that is these systems, at least initially, are not very predictable. They're not very deterministic. And if you go to a dyed-in-the-wool engineer working on safety engineering and say, Here's a safety critical system. If it goes berserk, 10,000 people will die. We can't really predict what it's going to do, but we hope it will do things well. It's not really going to work. But on the other hand, how do you verify a human child? Constructionist versus constructivist. So we've just covered a quick glimpse of some of the work that has been done. There's been a bunch of other works. Architectures, some people say, are about balancing stakeholder concerns. So of course you need to identify who are the principal stakeholders, what are their concerns, what are the characteristics of these systems, how do these architectures compare with architectures that already exist, and truly what are the implications of replacing a human being. How can an autonomous vehicle learn while it is driving, and how can you validate this learning on the go so that you can push it out to all the other vehicles in your fleet? What is the influence of implementation technologies? This is actually very important because often if you ignore the characteristics of a specific implementation technology and make your architecture in an ivory tower, it's not really going to work. And we have plenty of examples where a nice new implementation technology comes along and people are like, hey, this is amazing. Let's do it this way. And then you find that your architecture is basically collapsed because of that change. Similarly, modeling and representation is important. We've looked at different architecture modeling technologies and also tools. Because when you do real problems, you want tools that work. You don't want an academic theory. Although the academic theory is extremely important, it's only as good as the tool that you make available to your engineers. So the main challenges ahead are really related to verification and validation. Today you have companies like Google saying that we covered 1 million miles. But those 1 million miles were not driven with the same software snapshot. The software has kept changing. So there is no one software that has actually driven 1 million miles. And what the future holds is really your car is more like your cell phone. It gets updates very, very frequently. And the model in which manufacturers build cars today is broken. It's not going to work. What manufacturers do is they write their software, they test it a lot, they deploy the car, and then they try very, very hard to not change that car again, because that will trigger a big verification and validation process. But you don't want that. You want updates that come out daily. You want cars to learn something new and to utilize that learning, which also calls for managing things like complexity and so on. And I have to say that one of the main challenges ahead is not technical. I've been engaging a lot with the Department of Motor Vehicles in California for formulating requirements for testing autonomous vehicles on public streets. And the amount of corporate self-interest is mind-blowing, or maybe not. It depends on how naive you are. I was pretty naive. And I have to say that technological things are like the last thing which is discussed out there. So this is actually going to be important. We need companies to come together to establish common ground, common standards. And this is typically influenced by governments, but governments are then typically influenced by corporate and private players, and it's just a quagmire. So we need to quickly go back to the hypothesis and the research questions. Were they valid? And we will take this in the discussion, but the simple answer is yes and yes. The hypothesis was valid and the research questions were answered. The impact of this thesis, scientifically, there have been 4 journal publications, a number of conference publications, a book chapter, big vehicle prototypes were created. We were the only truck that successfully participated in the Grand Cooperative Driving Challenge, and we were in the 4th position. And some of the biggest industrial conferences in Sweden, it's Electronik Fordon, and the biggest conference on autonomous driving is Autonomous Tech AD in Berlin, and the corresponding Tech AD in Detroit. I was fortunate enough to be invited to these conferences to give a talk. There were a number of large workshops here at KTH and invitations to speak in European summer schools. 14 master theses were supervised, which incidentally is one of the highest for a PhD student, some coursework. And in 2014, when there was a deal between Saab and the Brazilian government, there was a delegation sent from Sweden to Brazil to explore joint cooperations. And I was one of the people in that delegation representing autonomous systems development for Sweden. And one of the big metrics to see how good your research is about commercialization. And two private companies were founded in Stockholm. They're still active for commercializing some of these research concepts. And a very big role was played in Silicon Valley as well. And finally, how do we continue the research? This triggered the formation of the Archer project, which is funded by Scania, engaging 3 new PhD students, and it's one of the biggest projects undertaken in our research group. So that was what I had, 35 minutes, and we can now have detailed discussions. Thank you.
Rich and vivid presentation of your thesis content. You reassured us here that you had actually used the right hypothesis and the results were valid, but I think actually this whole defense is about scrutinizing that. And to do that, I invite Professor Cherkovich to the scene. And as I said before, there is no time limit. You ask all the questions you want. So please make yourself comfortable and start the discussion. Most welcome.
Thank you. So I think that was because it takes some time. Because you answered very nicely, yes. You know, one of the things in the research is this criticism of
Excuse me when I interrupt. I don't think that you're hearing anything at the end here. So people will keep in mind. Could we have a? I know that the acoustics of this old church is actually very difficult. So in order to switch on that one, will that help?
Okay. No, it's not good.
Okay, why don't we take this one and I will speak.
There's another one. Maybe that one works. No, it works. Okay.
So, oh yeah. Okay, now we shall perform. Okay, thank you very much for your presentation. It was very interesting to listen to the presentation, and you addressed several things which are important in the research and which I really want to discuss with you. Before that, I would like to say like a summary of your work, how I have understood it. And I had a nice reading because the composition of the thesis is like you have introduction with some motivation and stated the questions, and after that you did the summary of the papers, quite extensive summary. So, and as you have written in the thesis, you could read this summary and then get a feeling what it is about in the papers. And that's true. So this way it's easy to read that part, and after that there are papers themselves. What I was also, and I will ask you later, was expected a little bit also complementary view to this paper. Some of them you actually others here in the presentation. So thanks for the presentation and the paper. And now saying this, I would like to ask some questions, of course, and to discuss. And you know, I think I will go like in principle from the beginning to the end of the thesis. And so that will be different type of questions, maybe some more general. I like to ask questions which is not possible to answer, so don't be afraid if you don't answer, but of course you should be able to reason. And there are some simple questions about from the curiosity. Why did you feel like that? Why did you do like that and not another?
Okay.
Okay, so let us start. So obviously you like automated driving or autonomous driving, or how do you call this, highly automated driving. And so that's one aspect of the thesis, definitely. The other one is obviously the title, reference architecture. Okay, and then when I start to read this, I had in the beginning a little bit difficulties with understanding what do you mean exactly by the reference architecture. And I found quite a lot of architecture terms. It was let me see what I found. Some of them: reference architecture, logic architecture, functional architecture, federated architecture, system architecture, hardware architecture, software architecture. I know also some others like deployment architecture. So there is a lot of this kind of architectures, and you have a nice figure that classifying this architecture to conceptual and technical, and then maybe you can show this.
Right.
I think you had it somewhere on page 6 or something like that.
So yeah, I can.
Yeah, but I would like to ask you, okay.
This one?
Yes,
Yeah.
but where is the reference architecture?
So yeah, absolutely. Let me just see if I can zoom in on this problem. This is not my computer, so.
Yeah.
How does one?
If you move the mouse to the lower right corner, the menu appears to
The lower.
the right corner.
Control plus.
Yes.
That's PC.
Right.
Yeah.
Okay. So your question was, how do reference architectures fit into this picture? Yes. I would say that a superset of the functional architecture constitutes reference architectures. What the functional architecture does is that it shows at a high level the main components in the system, the interfaces, their relationships to each other, and implicitly some of the solution patterns and best practices that should be part of the architectural instantiation. But a functional architecture for a specific project might not cover the entire set of patterns or best practices or stakeholder concerns. But if you make a superset of functional architectures for a given class of problems, that would become a reference architecture.
So it would be like another dimension in this picture.
Yes. So if you imagine that this functional architecture block has many other functional architectures blocks behind it, that set of functional architecture blocks would then constitute a reference architecture.
Okay. I was thinking that you had like the title about the architecture, but this reference architecture was a little bit unclear. Where how does it fit in this figure? But if you zoom out when we are here on this figure,
Okay.
And that's if you look at this circle.
Okay. I can zoom in on the circle.
Yeah, exactly. So you started like scoping the problem, I would say. Okay, starting with highly automated drive, and then you made a circle with like 4 main parts: algorithms, social regularity, system engineering, architecture, and then some function of that. But I was a little bit curious. Okay, why are you doing that in circles? And is there something missing here?
So why am I doing it in circles? It just seemed to me to be a good representation for a concept where you have something at the center and then you have a lot of surrounding concepts that feed into the concept at the center. So for example, here you have on the right, architecture and systems engineering. And then you say, what concepts lie behind architecture and systems engineering? For architecture, three main ones are representation, simulation, and analysis. And similarly, for systems engineering, you have requirements, testing, and V&D. And then I could have drawn another concentric circle outside to say, okay, what lies behind simulation? What lies behind analysis?
But I would say, for example, if you look at requirements, you have requirements on algorithms, you have requirements on architecture.
Yeah.
So it's not unique for the
It's not.
system engineering.
No, absolutely, it's not.
And similar with verification.
And this figure also does not show the very tight interrelations and dependencies between the different fields. And to answer your question, what else is missing? You could argue that things like sensors and actuators are missing.
No, that's a part of system engineering, maybe in architecture.
Okay.
But processes, and you actually mentioned on one later on in the text that from this picture you are looking at reference architecture and the processes. But I don't see here the processes.
Right. I see processes as an inherent part of systems engineering.
Okay.
So I abstracted that under systems engineering. The processes, methods, methodologies, and the tools and frameworks.
Okay, so that will come in this outer circle.
Yeah.
Okay, so my understanding was a little bit like, okay, that's your focus, you know, in this research, and I think that's okay. You say that's my focus, but of course there are also other things which are not in the scope of research or field work.
Now, I agree this is not the best representation. I hope it would be good enough.
Yeah. Okay, and I was similar puzzled by your picture. Okay, this is just a parenthesis. When you present your papers, so it's like a big circles, and there are like four circles, small circles. So it looked to me like a button or like a set of different things.
Okay.
But they were not overlapping.
Right.
And
Yes.
so I was thinking, why they are so separated? So are they really separated? Or, yeah, also, yeah. And yeah. So
I do see a distinct separation. I agree that there are some levels of overlap, and I should first point out that these circles are not really like Venn diagrams. It's just to show four broad categories of the contributions. Now, I will tell you why I separated scientific and engineering, for example.
yes.
Sometimes, okay, I'm not saying this always happens, sometimes it is easy to dismiss a report or a piece of work and say, but this is just engineering. What is new in it? And that led me to think that if you get into tiny implementation details, that becomes too engineering because it's not general enough. So there was a report on the technical aspects of the truck project, and that was considered engineering. And then the things that could be generalized out of it was considered more sciencey, and so it went into the other bucket.
But the state of the art and industrial challenges, so you don't see that as scientific.
Depends on how you define scientific. But I know that the state of the art is definitely one of the early steps in any scientific process. So perhaps it should have been under scientific, but then maybe that would have not emphasized that this was done as clearly.
Because so what do you think the most important state of the art? What is the most important role in the research process? You said that it's an early.
First, it is to understand what others have done and to find promising directions for things that have worked, and also to understand what others have tried that has not worked. Because earlier in autonomous driving, people were using magnets and steel rails, and that approach has quickly died out for a variety of reasons. Similarly, if you even want to think, is cooperative driving worth it? And you find a state of the art that says, I've done a simulation and it shows that there is a potential to improve fuel economy by 10%. And then you're like, aha, this is definitely something worth doing. So that is one reason that you would do a state-of-the-art survey. Another very interesting reason, maybe which is not so technical, is to find potential collaborators. When you see someone who has done a very nice project and you say, okay, let me check out that person's website, what are they doing? Maybe I can work with them.
Yes, but there is one element important in this state of the art, and that's okay. So you analyze and you mentioned it implicitly, you continue to build on the state of the art. And then you compare your results with the state of the art. So that's one very important element. And so you have mentioned many times prototypes. So what would be like validation, a difference validation on prototype level and validation in comparison with the state of the art?
Absolutely. I have to start off by saying that most of the state-of-the-art in autonomous driving is still about prototypes, because there are no production autonomous vehicles out there. So this actually helps, because then you can make an apples to apples comparison. And the main state-of-the-art today has been things like the Mercedes-Benz S-Class vehicle, vehicles from the DARPA Urban Challenge, and Google's vehicles. And what we do is we compare what we have done with what they've done to see the similarities and the differences. Now,
but what about reference architecture?
I couldn't find a reference architecture for autonomous driving. I looked very hard. I found reference architectures for autonomy in general, in robotics for sure. The only other work towards a reference architecture for autonomous driving that I'm aware of is something that I discovered after this was sent into publication. It is the work being undertaken by Dr. Steve Underwood. They have just 3 months ago formed a committee under SAE to create a reference architecture for autonomous driving.
Actually, there are some work in reference architecture, maybe 5, 6, 7 years old, only embedded system, for example.
Yes.
So I would expect a little bit more also comparison about your approach, okay, how to define the reference architecture, what kind of reference architecture to exist, and make a comparison with the state of the art. So in that case, you're right, so there are not many work on reference architecture with automated driving, but there are in different areas, related areas, you mentioned robotics and definitely general systems. So that would be a nice, both from a validation point of view and also kind of research contribution. So that's why I will put this circle, I will put them more close together.
I should point out that actually the most amount of material I found on reference architecting in general comes from Dr. Müller, from the Architecting Forum white paper that you have on reference architectures.
Okay, and then if you go to your hypothesis, then of course, so that's related to hypothesis and the questions. You can state a question or make a hypothesis which is like a simple proof, simple realize and say yes, yes. So here is the question. So if you ask like a reference architecture for highly automated driving exists, and then you have put, okay, I made it, so look, it exists. But of course, that's kind of very simple, simple, I wouldn't say, okay, trivial, but you said it. But then you have some addition, which make a lot of scope. And you say it's general enough to be repeatedly instantiated and to provide sufficient solution for a variety of automated driving tasks in a variety of scenarios. And that's scoping much better, but I still have a little bit problem here, which is general enough and provide sufficient solutions. So do you think that you have proved this hypothesis, or maybe you can say in which way you think that it is general enough, or maybe you can also say when it is not general enough? Yeah.
Yes. So I believe that the hypothesis could always be falsified. It's in a sense like an NP-hard problem. Unless you consider every single instantiation and prove that it works for every single instantiation, you can't say for sure that the hypothesis has been verified. So what we have now is honestly a working assumption that it works. And the reason behind that is we've tested on 4 different prototypes, and the hypothesis was formulated prior to those 4 prototypes being created. So in our own experience, the 4 prototypes that we created really were very, very different. It wasn't an incremental change from one prototype to the other. One was a truck with legacy, the other was a vehicle that didn't exist 4 months ago. So given the diversity of the prototypes that we created, that is one reason to think why this hypothesis could be valid. The other is, if you look at all the state of the art that we've seen and the other prototypes that people have created, and see, can the solutions made by other people be recast into a reference architecture? If I go to Volvo and say, what is your architecture? And then can I map what they have done into elements of my reference architecture?
But did you do that?
Yes. During the Fuse project.
Okay.
Yeah.
So, but did you then change the reference architecture?
I didn't have to. It just fit in very neatly. Which is another reason why I claim that the hypothesis is valid.
Okay. Okay, so.
I also checked with the Stanford University, and it works.
But who said that it works?
I said that it works. I should have asked other people. But the fact that I went there, I explained my approach, and they said, would you like to now come and work with us? Because we think this is amazing. Let's start a company around it. And the fact that the company has gotten a lot of interest is another indirect, admittedly, reason to claim that people agree with my system.
I can ask you also another question. So if you give to someone, you say, okay, this is the reference architecture, so you can instantiate it. So do you think that other competent people could do it?
Yes, absolutely. The first cut of this reference architecture was presented at a workshop in Montreal, in Canada, and it was, people liked it. They considered it to be among the better papers, and they asked me to submit an expanded version to a journal. So there were about 15, 20 people there from different automotive companies, and they came up to me and said, this is good to start a reference architecture on this topic.
Okay, although you know, to write a paper is not the same as proving that.
No, it's not.
But you have very nice description, I think. Which paper was it? The third one, how to instantiate reference, papers from the reference architecture. It was very detailed, so I believe you at least that a lot of things can be done. But then, of course, you know, okay, there are a lot of things here. It's also a question that what is done, is it correct? And then it's a question, what does it mean correct? But okay, let us go further. When you start to talk about when you in your paper, okay, paper A, you mentioned that you had a workshop and discussed about obstacles to design highly automated driving for autonomous vehicles. I was a little bit surprised in the introduction. You talked about the obstacles, and in the paper you are talking about, or you are mixing obstacles and bottlenecks.
Mhm.
Do you think is that the same, or there are some differences?
That's an interesting question. I have to admit that I use the terms synonymously, obstacles and bottlenecks. And now that I think about it, since you raised the topic, it seems more like bottlenecks are things that slow down and obstacles are things that prevent. So,
Yeah.
my bad.
So-
I used obstacles when I should have said bottlenecks.
Mhm. I thought the opposite, that you actually talked about the problems, not like particular part of the process which should be improved, but some principal problems.
Well, yes and no. I think we've identified about 5 big problems.
Yes.
And now I'm using another term, problems. Some of those are obstacles and some could be considered bottlenecks depending on how you interpret the terms. So things like managing complexity, I wouldn't really call that as an obstacle because we already have complex systems. It's just a lot of friction. But other things, I can just go back and show.
We'll come later to details about the paper. So this is more like a principal question. Okay, you have obstacles. You mentioned bottlenecks. You have problems. You have challenges. So there are slightly different things. So probably bottlenecks are something which already exists in the process, while obstacles can be something which prevent you to do something. That's maybe related to problems and challenges. But okay, that was just a short comment. But I will come later to some little questions about the paper. Before that, I would discuss a little bit the research method with you. So it's more general, and then okay.
We can go back.
To that one, and you call this research type, like engineering design, and you explain, okay, this is about we construct something, we do something completely new, and okay, then we have to validate. So probably we cannot validate in the same way as in natural sciences, when we have the facts and we have to describe it and validate knowledge about that. And this is, I think this is okay, but still I was a little bit missing about what is the difference between engineering development and the research.
Okay, I'm very glad you touched on this. It's been a favorite topic of mine. And engineering design, this research method is actually described in a paper by Timothy Ferris called Engineering Design as Research, in which he goes into great depth about the differences between what constitutes engineering and what constitutes science, and the differences between them. So for me, engineering is about finding sufficient solutions to a problem. Maybe not the best solution, maybe not the most optimal solution, something that is sufficient. And then you can discuss what sufficient means, which is part of the engineering design study. And research is described as the activity that creates new knowledge. And when you make a prototype that did exist before, what you've done is you've created new situated knowledge that says, how do you solve a particular problem? What is the knowledge necessary to go from requirements to a product that works?
Yes, but that's also engineering. So the research would be, I think, 2 things here. Like you mentioned.
I have to add a few more things. So that in itself generates new situated knowledge, But in order to really elevate the scientific heights, you need to look at it and say, what were the principles? Can it work in a different context? Can it be generalizable? Can it be reproduced by others? And that is something that was very important to us. And one of the weaknesses of engineering design is the so-called external validity, because you've tested it on the prototypes, and of course it works. And that isn't sufficient to claim that it is valid. So we balanced it with expert interaction. For example, none of the prototypes that were created were created by looking at what other car companies were doing. But once we did that, we had a discussion with architects from other companies and said, hey, this is what we're doing. What do you think of it? And try to get as much external validity as possible and generalize it. So, yeah.
Okay. Yes, you are right, and I agree with you. I think also is important in general in the research, in this generalization, to define the scope. So what is general and what is not, when it is valid, when it is not valid. So if I ask you, for example, for your work, this you said you have like tool reference architecture you have developed. So what are their limits?
Right. So we could actually go into the paper, because in both the papers I describe under what circumstances the architecture will work. Typically, for the reference architecture on cooperative driving, we make certain assumptions on what feature sets are already available in the vehicle. So, for example, in the GCDC, we had an adaptive cruise controller that was already present in the vehicle, and what our layer did was it gave set points to the adaptive cruise controller.
But then the question about the generality would be, okay, your reference architecture, would it be valid for any type of cruise controller?
It won't. There is a set of delimitations. So if the vehicle platform meets those conditions, only then will the architecture be valid. Otherwise, it might not be valid. It is the same for autonomous driving as well, because if you look at the leading vehicles for today, they have almost functions like autopilot and traffic jam assist. And we heavily count on the fact that such functions are present in the vehicle, or at the very least things like traction control are present, because our reference architecture includes no elements to take care of things like platform stability.
Okay, that was a little bit my comment. I thought that in the introduction part, you could have others more explicitly, okay, what are the limitations and what is the scope, what are the assumptions. You had it in paper,
Right.
but it was more concretely related to particular programs in relation to reference architecture. For example, I can ask, when you had a place like timing issues, is that a question of reference architecture or not?
That's a good question. I would go out on a limb and say it's not really, because it depends so heavily on implementation technologies that beyond saying that you need to identify your timing requirements and make sure that they're met, there is not a lot of things you could say related to timing.
But many functions, to function architecture, are heavily related to timing issues.
Absolutely.
Maybe not only to real time in the sense to reach deadlines, but also synchronization, something happening at the same time.
Right. So you can define sequences for function execution, and those are implicitly defined in the direction of arrow flows. When I said you can't have timing in the reference architecture, I was thinking more of hardcore implementation technologies. Yeah. And then it's like, if you don't know what algorithm is running, then you don't know what its timing requirements are, and then you can't say what microcontroller to use and what communication bus to use and what its bandwidth should be. So that, for me, rapidly becomes instantiating specific.
So that's also related to this question about, okay, what is a part of the reference architecture? And, so I think one part of the research or the knowledge is, okay, how does look like reference architecture, what should we include, what should we not include, should be part of the research. You have a very nice description of how to instantiate, but I have not seen, okay, how did you build? It's more like, okay, I have this knowledge, I repeat this knowledge, and that's that it is. I think what would be interesting, that's maybe related to your paper, okay, like more in general, okay, the questions which concerns are part of the reference architecture, which not. You have mentioned it in several places that, but that will be one type of research related to the reference architecture.
Yes, I completely agree. It would have been good to explicitly mention that in the introduction and the papers.
Okay, let us go to this already part of your B&C papers, platonics, cars, which you show very nicely follow each other. And then in your paper B, in the scope, you have identified a number of requirements. And I can mention that you could say separation of functionality to self-contained logical units. The second one, enabling of runtime reconfiguration of intercomputer and component communications. Third one, permitting different algorithms to be swapped. The fourth one, enabling diagnostics and self-monitoring services. Then allowing changes to the run systems and being minimally intrusive in the existing vehicle architecture. So that was on page 25. And then I looked at it and I thought, okay, which of these requirements are specific for automated driving? Is that not many of them requirements for complex and safety critical systems? And in particular, I see several which are related to dynamic deployment, or if that is dynamic deployment, or was it static deployment? You say, okay, enabling runtime reconfiguration, but algorithms to swap, that's also, is that a question of...
These are general concerns.
Yeah.
They might achieve greater importance in the context of automated driving. And I think, are you looking at the introduction? Because if you look at the paper itself, they are classified in far greater detail. It's about 20 of them. And what we do in the paper is we say which are specific to autonomous driving and which are more general. So that classification is actually present in paper C. But looking at this, I will agree that these are applicable to general complex systems. Whether they are important is an open question, but they are definitely important for autonomous driving. Especially when you are prototyping, you want to be able to pull out one path planning algorithm and put in a different one and still have it work as well as possible.
Okay, that's valid for any type prototype. But you have specified those which are really specific for, in this case, for collaborative driving. And then we go to this reference architecture. Maybe you can show this figure.
Right. This one?
So yes, and here I have some general questions, some complete questions. So first, okay, you decided about your elements. So you say square is rectangle is architectural element. So explain what is graphical logic mean, not directly arrows, but I was wondering, haven't you tried to use some modeling language?
Yes. We tried to look at UML and SysML.
Yes.
Later, we also tried to look at a tool called Capella, which follows a methodology called Arcadia. and we also tried to use enterprise architect.
Mhm.
And honestly, it still felt like this was a better approach to communicate, because the intention of this particular representation was to communicate the big picture to a number of people very, very quickly. We had 4 months in which to do this, and there is an effort needed to use a formal tool to represent your architecture. And in this case, it was considered that the effort was too much. And I would still say that unless you are a huge organization, my personal opinion is today's tools are simply not there, because when I formally model an architecture, once it's modeled, I want to do a lot of different things with that representation. I want to use it to communicate ideas, number one. Number two, I want to use it for analysis, for properties like safety and so on. And number three, I want to use it to actually generate a running implementation.
Okay, now I have. So I would agree with you for the first reason,
Okay.
and that in many cases is a criticism for many languages, architectural definition languages, or such that they are not expressive enough, or they are too expressive so that they cannot provide this message of easy understanding.
Right. And the tools also have a steep learning curve.
Yeah, exactly. But you said two other things.
Yeah.
It surprised me. You said you can generate. I don't can generate from here.
From this, I can do that. So the reason why I did this is this was the quick approach.
But you cannot you know, it's this is Ellipse, and say
It's a plugin.
generic plugin.
Mhm.
Yes, I don't know how to generate.
Okay, let me clarify that this representation does not generate running code, nor does it do analysis. It is only used for communicating the big picture to other people. So I'm not claiming that this generates code. To give you an example of what generating code is, if I model my architecture in something like Simulink, for example,
Yes.
and then I use something like XPC target or DSpace, I basically press one button and I get a hard real-time executing system.
Yeah, but then you have formal definitions of
Right.
your architecture language.
Yes. And the reason why I would be happy to formalize it in Simulink, and we actually did formalize this in Simulink, is because there was a great deal of utility from that formal representation. I could have shown a screenshot of the Simulink model. We can blow it up.
But when you did the Simulink, you actually manually mapped
Yes.
your picture to the Simulink.
Absolutely.
So I was still a little bit surprised that in spite of this requirement for explaining easy and send like a message not to use some of the formal
Yes.
languages for specification.
Mhm.
But that's interesting. So I have, for example, a question. Okay, why did you mention plugin here at all?
Okay.
Why plugin is here?
Yeah. The reason is that you want to take control, for example. You want to run different algorithms in that architectural element. And the technical way of doing that is to create each algorithm as a plugin and load that plugin inside the component. So that is why you have the ellipse, which represents a plugin. So you could have a PhD controller or a...
So I mean you have several variants of the same functionality.
Exactly, with the same input-output interfaces, similar timing interfaces, and different algorithms.
Okay, but that was not quite clear. That's not clear from this figure. Plugin can be okay. I can just then upload. Why it is and why it is not? It's not precise. That's always problem with such presentations, and then maybe they are perfectly clear to you, and maybe in a certain community, but could be difficult to for other community.
Absolutely. What it makes up in speed, it lacks in formalism and precision.
Yeah. So that would be nice. I think would be nice also to show in some way what you mentioned. Okay, you did it. Then when you come to the implementation, what is this bridge between reference architecture to like a formal architecture? So you mentioned there you defined how to instantiate. You said all elements. But you did not provide the formalisms how to do. So that which you basically did in practice. So that would be also one part of further research how to automate this process and then come to this model-based model-driven development or model-driven engineering. Okay, so similar is my question was here semantic data analyzer. I think I understand what it is, but maybe you can explain.
Yes, absolutely.
Yeah.
So it analyzes the different messages that are coming over the wireless, and it sends those messages to the supervisor, because the supervisor is the part where you're really trying to say not just what the messages are, but what do they mean? What kind of, for example, feed-forward actions that you might want to make, what kind of preparations you might want to make and send messages to the different components. So you have a pipe that passes it straight through the world model, but then you have a early analysis to build a better view of the world.
What I have problem here, you have this Arab to supervisor, and you have supervisor which it's
the entire canvas on which it's
so it's what does it mean this Arab? Where does it go?
So this is a bad representation for that part. I actually agonized over it for a very long time. The supervisor in an implementation is a discrete component, as is the semantic data analyzer, and the arrow goes into that discrete component.
Okay.
In this representation, it's shown more as the supervisor is the canvas on which the entire architecture is painted. What that means in practice is that the supervisor has high bandwidth bidirectional communication links into each and every component.
To every component?
Each and every component.
Okay, not to world model. And, this. No. So it also has to do local sensors? And...
Yes.
Okay.
So for example, well, not the sensor itself, but the component that abstracts the local sensor. So you want to know, for example, is my sensor still healthy? Or is it not healthy? And if it is not healthy, maybe I need to change the inter-component communication.
Okay, of course, that's also the question of design. So probably if you want to make more layered architecture or more abstracting, then your world model will manage the sensor and supervisor will communicate.
Right, but if you start managing sensors from your world model, you're kind of abusing its functionality, I would say. So for me, the world model is two kinds of things. It's a passive world model or an active world model. A passive world model is just like a data store, it's like a dynamic database. And an active world model is that which understands, for example, the physics of the objects which are in it.
Yeah.
So in an active world model towards which we are actually moving, it will know that this is a car and this is a motorcycle, and you can tell the world model, if I give these inputs or those inputs, how will the world evolve in time? And then you have 10 different possible futures based on the capabilities of your world model, and then you can choose this future is better, and then you choose that option.
Yeah. I think that's of course that's always a question of approach and the design. Probably there is no final answer.
No. And there is no correct answer.
Yeah, probably if you reach everything, then you lose kind of abstraction. Okay. So that was to my question. But then again, if I look, so what would be specific here for automated driving?
Things like map matching.
If you look like a robot, for example,
Well, autonomous cars are robots. Essentially, they're mobile robots.
Yes, yes,
Things
they are
like
mobile.
map matching is very important
Okay, yes, yes.
because you need to know where you are on a map. And then it really is about things like the vehicle gateway that is absolutely specific to vehicles.
Yes.
The concept of local sensors and super sensors could possibly apply to a lot of other things.
Mhm.
The HMI content would be very specific to the kind of vehicle that you're operating in, and the others are generic.
So what would be interesting to see if this reference, if you could define the one level more abstract for adaptive system, for example. So, but yes, okay. So let us. Then, of course, this is the function architecture, and you have mentioned that you did not consider. You did later talk about non-functional properties or
Yes.
extra functional properties. And, so I have here two questions. So do you think that reference architecture should address extra functional properties? Doesn't your reference architecture doing?
It should,
And
it should address extra functional properties. The reference architectures that we've represented in this way do not explicitly address those because they only show the functional properties. So for example, you can have a functional architecture that will show what are the main components and how do they interact when everything is working fine. But they will not show how it will interact when one of the components stops working. For example, does the control block over there need to be redundant? So when you do safety analysis at the functional level, ISO 26262 calls it the functional safety concept. Then you show how the architecture at the functional level can still assure certain properties. And when it comes to safety, for example, there are layers at which you have to analyze safety. A reference architecture cannot analyze them at all levels.
yes, but you know, many extra functional properties on one level they are implemented by some means which are functional.
Yes.
And many architectural designs are related from the beginning to particular extra functional properties, particular domains. So I was a little bit surprised that also non-functional requirements or extra functional requirements are not involved in the process when building up the reference architecture.
You are right. I would say that they were involved, and then I would point to the delimitations here, where I actually explicitly state that things like safety have been considered out of scope. Simply because
exactly.
I didn't want to sit and write about that, because the moment you get into safety, it becomes a whole different rabbit hole. But yeah.
But then you actually mentioned several places that you
absolutely
did care.
Because safety is important, we did care for it, and we show in different places some examples of how we care for safety. But if I had said we've looked at safety as well, that opens the door to a floodgate of questions which I wanted to avoid. So in the thesis, we made a delimitation. We are not going to talk about safety.
I agree. But then related to that also, which is I think addressed in the paper, KE here, model-based system engineering. You have a nice picture. It's nice. You have like top level requirements, and then next level defined requirements, and then you have architectural representations, and then application software components. So I suppose application, and then you have platform. So it's really top down.
Yes.
Does it work like that?
No, it doesn't.
Okay.
But there is actually a very nice paper that says the importance of methodology and the importance of faking a methodology. So this works in a very good way to communicate how an ideal process would work. Practically, you start top down because you need to have a big picture. You can also start bottom up and you meet in the middle and then you iterate a few times. So it is definitely not in practice a very clean top down method like that, but it's a useful representation.
Mm-hmm. But I was thinking, you know, if you start today, in most of the cases, you have products, and what you do, you are building up new functionality, like Google or something like that. So you actually start from something which exists. So there is an architecture, and then you want to add the new functions. So how does this model-based approach, this top-down, fits to that?
What you do is you start top down, you have your architecture blocks, and then you see how they can map to elements of the existing architecture. So in this case, the control, for example, was mapped to the adaptive cruise control block, but at the same time, I have to say that we knew there was an adaptive cruise control block. So that kind of front loads your thinking at the top down level. And while it is very true that we do have existing platforms, at least I've been fortunate enough to begin with a clean sheet design with zero legacy whatsoever. And there the top-down approach really helps, but not always. So for example, in one of our cases, we were thinking, okay, we have 12 cameras. There is no way we can send data from those cameras to a central computer. So let's have an architecture where we have small processors next to the camera that processes the camera data, reduces it and sends it, because that brings down the requirements on your network.
So I would say like that. So your view is a view of system engineer, definitely not as software engineer.
No.
So in software engineering, you know about the most popular methods of today, agile methods, which says, okay, you have something, you want to add something, you do it very fast, and then you see done, and then you refactor.
Right.
But at the same time, there is a lot of discussion today about how to improve the processes, how to digitalize the production, and so on, and introduce software methods. So what is your view on that?
My view is different strokes for different problems. Definitely starting quickly in software is good. Refactoring in software is feasible. Refactoring in mechatronic systems is not always easy, because if I start bottom up and I build my board and I build my processor and I give an I/O, and then somebody comes and says, you have only 24 I/O, I need 48. Refactoring that is going to be a big problem. So there are times when software you can say, just do whatever you want, we will flash a new version of the software later. But when it comes to safety analysis and electronics and things like networking choices, should I use a canvas or do I need gigabit Ethernet? That's not something you can refactor as easily. So there you would need top down.
Yeah, it's also a question in the modeling. If you have a model of that, and then you do a new version of a model, and then you do bottom up. Start from the existing and some changing and get a new model, and now, okay, so you do on the model level what you can do in software. But this is a challenge in general. Okay, then I come now to the papers, and you have covered many things in the beginning. These papers, so here you have some maybe more questions on some details. So the first paper you described these challenges, obstacles, bottlenecks, and you said it was a result of discussion from workshop. So what I was missing in the paper, and was a little bit more precise specification. How did you come to these results? Who were these experts? Why should I believe that it is like that? So not you get like a paper for review.
Yeah.
One guy say, "Oh, we had a great workshop and we come to this." Does not work. So did you have some methodology how to get the findings from this workshop?
Yes. So first off, you should not take it on faith that we had a workshop and we came. So you're absolutely right to question it.
No, I believe you. I believe you. It's a principle.
Yeah, exactly. We used the World Cafe method. So we had about 70 engineers who were coming in, and we split them into a number of different rooms. Each room had a particular question, and each room had a moderator. And every 35 minutes, everyone except the moderator rotated in a circle. So at the end, every group had discussed every question, and the moderator had heard the views of every person.
Did you state the questions?
Yeah, so we prepared the questions in advance. I don't have the list of questions with me right now. I could probably pull them out. They are there in the workshop description. And I was one of the moderators. Martin Jörgen was another moderator, and we had a few more. So after going through the World Cafe sessions, we came back to collect the resulting learnings, and then we had a second round. And out of that, distilled came out these questions.
So you usually, in such empirical research type, it's very important to describe the method and also to critically analyze validity of the findings.
Yes.
So who says that maybe there are people from the same company who are having just a particular problem and they are thinking of that and they answer the same, and then you get answer, okay, 100% of people are saying the same thing, so that must be the truth. So the validity of findings must be discussed, generally in the paper. So that was
absolutely.
But this was also okay.
We were hoping to actually make a journal paper to describe all of this. In that, we had a strict limit of 8 pages.
Yeah.
So we chose to, prioritize the actual content. But you are completely right.
So for journal paper, definitely that would be needed, and then also reference to the actual questions. So that it is. But then related to this, which you described here, see. Okay, so you had some things like you call them bottlenecks, let us say challenges, constructing and maintaining the world model, and that's kind of intuitively clear. The vehicle must have some model of the world which otherwise is driverless. So that's clear. Okay, this is good. But then you come to user interaction. Okay, is that specific for this type of problems?
It's specific for autonomous systems, actually.
But it's also for any other. For driving cars, it's also user interface is important.
Sure, user interaction. The word user interaction, sure, everywhere there is a user, you have user interaction. But the content there really talks about the trade-off between how much the user needs to be engaged in the actual operation of the vehicle, and that then starts becoming more specific to autonomous systems. Because, in fact, I think 2013, the Federal Aviation Administration said that the number one threat to global aviation today is not technology, it's not terrorism, it is pilots losing their skills because of over-reliance on automation. So the question that you don't want the pilot or the operator, but you still want them to have the skills, this seems like an almost impossible problem to solve.
I agree.
Yeah.
But then the next one, complexity and feature interaction. I mean, that's for any complex product, and for product lines when you have many variants, this is like clear. challenge. So what is specific here?
It is
It
not
has-
specific to autonomous driving. It is important for autonomous driving because the potential consequences can be more catastrophic.
Yes.
The feature interaction actually came up in telecom domain, but the worst that will happen is you won't have access to your phone. Whereas if you have it in a truck, you could have a potential impact.
Yeah, but that's also with heavy drivers.
Yes.
That's it. And also with extra functional properties.
Mhm.
It's similar. Of course, the difference is how to then implement the means, how to manage. But then you mentioned the redundancy.
Mhm.
So redundancy, you may call it extra functional property, but is that a property really,
It's not.
or is it solution? Is it
It's a technique of assuring certain kinds of reliability and safety.
Exactly. So maybe I wouldn't call that like your property, but this is a typical way of means of solution for as I mentioned, like reliability, safety, availability, and then of course there are specific challenges how to implement that,
Mhm.
and also. I was a little bit puzzled by this determinism and predictability, and on one place you said like that, ideally safety, in the safety analysis you don't need to use the context. How was it? Does not, that safety does not bother about changes in the context.
Can you point where I read that? Safety absolutely depends on the context.
Yeah, I was, exactly. I was very surprised by that.
Yes.
Okay, let me.
Okay. If
Maybe,
you find
maybe
it,
I
because
find it.
yeah.
It's a little bit detailed. Yeah.
Okay.
But the question is actually what I want to ask is you have safety requirements and you have robustness and predictability, but then on adaptive systems you have actually another important property.
Mhm.
Do you know which one? Yeah, there are some.
I don't know what you're thinking of, but yeah.
Like resilience.
Right. Okay.
So ability to adjust to the changes.
Mhm.
So you haven't discussed that.
Yes, I haven't. I've touched upon it
Yeah.
in the constructivist versus constructionist approach. But what I meant more by safety here in this paper was the fact that typically you want your behavior to be deterministic. But most of the algorithms used in autonomous driving are probabilistic.
Yeah.
And you cannot guarantee or predict their behavior. So we actually, let's say that you have a path planning algorithm. One of the popular path planners is the RRT, rapidly searching random trees. And the only guarantee you can make about it is if a solution exists, if a path exists, and if the algorithm is allowed to run for infinite time, it will find that path. It makes no guarantees that you will find it in the next time slice. So if you want to implement an algorithm like this in a safety critical system, and you can't even guarantee that it's going to find a path which exists, that is going to make safety people very uncomfortable. So the question is, when you have a lot of probabilities, when your classifier says that's a pedestrian, but I'm only 65% sure.
Yeah.
Okay. So how do you balance determinism versus the inherent fact that if you run these algorithms, they are not going to give the same results. You can have the same algorithms running on two different computers because of different random seeds. You could have them coming out with two different trajectories, same code.
Yes, this is definitely a challenge. Okay. So a short question related to your second paper, the team scoop.
Mhm.
I was just curious. you did it with trucks.
Yes.
Okay, you show pictures. Your truck was between other cars. So, was your design for following, for collaborative driving? Did it included specific parts for trucks?
It did. It left most of the truck-specific parts to the truck itself. There were some parts where we actually did consider some of the characteristics of the truck, and that was in the control. So when you follow a vehicle, the vehicle can accelerate at say 3 meters per second square. And a truck has many different gears. So it takes time for the truck to go from one gear to the other. And we tried in our control algorithm to predict what could happen so that we could be in the right gear in advance. It didn't really work, and that was the reason why we ended up in the 4th place. Because sometimes the lead car would accelerate and we would be switching gears. So if you plot the graphs, you would see the velocity of the lead car is going like this, and our truck is doing nothing, and then it starts accelerating. And yeah, that was just how it was.
Okay, yeah. It's always a question if you do like reference architecture for a particular type of system, can you really isolate those parts which are specific for that type and the rest have maybe more general? That's one.
I believe that is possible.
Question. Yeah. Okay, and okay, we talked about this reference architecture quite a lot. Yes.
I just want to point out, time check. We can do this indefinitely. I just know that this room has another PhD defense at 1 o'clock, and someone is going to come for it at 12. Yeah, I just leave that to you to handle. We can keep track.
We can move.
Just go ahead.
Okay, there was my comment here, my question. So when you have these guidelines for instantiation of the reference architecture, you have like grouped how different steps, how to instantiate for different elements, but I have not seen the process. So if I would read like that, I'm not sure if I could do it. Do you think that the role of this reference architecture is also to describe the process?
It could be, but in this particular reference architecture, we've not paid attention to the process as much. We're focused more on the what rather than the how.
Yeah, exactly. Which of course is the first step, maybe like that. And we also discussed a little bit about this model-driven engineering. Okay, here I see my question here. Do you think that it would be possible to make reference architecture for a particular domain, from which you can automatically, with some input, generate architectures, different architectures?
It depends on what you mean by different architectures and what format. If you want to make block diagrams, sure, it would be possible. You can have architecture formally modeled, which is a superset, and you can provide some inputs, and then it will generate a number of architectures and tell you how they evaluate on different metrics. That, I think, would be possible. The tools don't exist, but they should be very easy to build. Very easy, but yeah, it should be possible. But going from a reference architecture to an implementation and having a generic representation of such a reference architecture, I don't see it happening at least in the next 5 years, given the tools that we have to do.
5 years.
At least. Definitely not.
Related to that, I would like to ask you, some years ago, Martin, we had a paper, and he is like a model-driven engineering guy, like component-based, and so we thought about, okay, how you make like new products, and this model-driven is more top-down.
Mhm.
But like in component-based, you have components. So you have many of existing things. So would that mapping of your reference architecture to the existing systems, and then providing the information, okay, what have you to change or to add, would that be possible?
I think it would be possible, but it would involve a lot of manual work by someone who really understands the existing system and where you want to take. So you can always encapsulate existing functions, legacy functions, and put gateways through that. But I would say it would be a lot of work.
But you know, most of the work in reality starts from the existing systems,
Yes.
not from the scratch.
Yes.
So how does it make a problem then for reference architecture? You don't need them because.
I think there is still a lot of value in having reference architectures, because what you can do is, sure, you have an existing system, but you also need a goal to where you want to go. And that is what the reference architecture helps you with. It's like a mental model. And once you know that, then you start thinking of a process to migrate from where you are today to where you want to go.
But in your model, I have not seen this from where you are starting.
Right.
It looks to me, okay, you are like showing where you want to go, what is the goal. But I don't see like this, okay, I'm starting from a particular current reference architecture, I want to add something, or I start with a particular architecture, and there is some reference architecture, how it should look like, and how should I combine this.
Yes, I have not shown that process. When we were working on the truck, you obviously had some very, very hard constraints. When we were working on something like the RCB, we had almost no constraints. The architecture was generic enough that it could be applied to both kinds, but it required a lot of manual thinking. It would have been good to have it, the process, but we did not.
I think that would be interesting research. Okay, which actually you did in practice. You took Scania car, truck. You know, you start from the existing physical hardware architecture and a lot of software architecture, and then you add your additional components.
This was the hardware view. We only added two things to a commercial truck, and I think the only change needed for the truck was that the adaptive cruise control gets disabled below a certain threshold of velocity, and we reduced that threshold down to 0 so that we could use it at any speed. But other than that, it was a very plug-in system. You take a truck that's rolled off the assembly line, plug it in, your performance.
So I think that there can be further work related to the reference architectures. So not only how they look like, but also how do you build them. Okay, so now I started a look about the time. Okay, I had here some questions, but they're not so important.
I'm pretty sure we can go through all the questions. Max said he's going to manage the.
Don't worry. So last year I had like, I think, maybe 10 defenses.
Okay.
So, no problem. And I enjoy to do it, so I can do it like for hours.
Challenge accepted.
Yeah, I'm enjoying. Okay, I was a little bit curious when you talked about the functional architecture, and that was your paper this functional reference architecture for autonomous driving, is it D or
Yes,
E paper?
it is paper D.
D, yeah. And then you have like two figures.
Mhm.
And on the first one, you wrote like distribution of functional components across the layers. And then a little bit later, another one. And the first one, I haven't seen any relations. I've seen like different functions,
Mhm.
but you know, they are squares,
Mhm.
rectangles, and then the names of different functions, and that's it.
Right.
So to me, it looks like that's the same as you have in the list.
Mhm. Yes.
But later, you actually provide the relations between.
Yeah, absolutely. So
Yeah.
what I wanted to show in this diagram, and maybe I can explain to others.
Yeah, maybe you can say which page is it.
Where it is, yes. So if you go to paper D, it's on page 15 of paper D, figure 4. So what I try to show here is not so much the relations between the different components, but there is a dotted line here, and what is below the dotted line is in the vehicle platform, pre-existing, and what is above the dotted line is the artificial driving intelligence. And it's always an interesting question, given that you have these two relatively distinct layers, the vehicle driving platform and the cognitive intelligence, which is essentially replacing the human, how much functionality would you put in the vehicle platform and how much functionality would you put in the cognitive driving intelligence? And there is a continuum and there are two extremes, and this figure shows the two extremes. So in the right one, there is a lot of functionality in the vehicle platform, which is in B, and in A, there is almost no functionality in the vehicle platform.
But for me, it looks like it's not like functional architecture. It looks to me like a deployment architecture.
Oh, it's not even an architecture. It's
it's
just the distribution.
Yeah, you're right. You're right. But then when we go to the next figure, which is figure 5,
that is an
which
architecture.
is yes, but here also you have a little bit like mixing some system architecture elements and software architecture elements with functions.
Okay.
I think that is a challenge because you have like a list of you have here like sensors, sensing. You know, you have this line.
Yeah. So the line is the dividing line between the vehicle platform
Yeah,
and the cognitive driving.
exactly. So it's not pure functionality.
No. So this architecture shows 3 layers. Point number 1. It shows how the components are distributed across those layers, and we also provide the ratio. And the third thing it does is it shows the interconnections between
When you say components, you know, what do you think about what the components are? Are they architectural elements of the structure, or are they functions?
These are elements of the architecture.
So you see that actually in this functional architecture, it does not show all the functions, and it does not show relations between functions. So you don't have relation between stability and braking, but you have actually the relations between components, which are architectural elements, which goes to implementation.
Right.
So this functional architecture is not conceptually quite
It's not completely
clear.
clean.
Yeah.
I would say yes, it does mix up a few components. The thing is, I agree with you. When I speak with different architects, the meanings of the words elements, functions, features, and components changes from person to person, from company to company. What one would call a function, another would call a feature. And you are a software component person, so I guess you have a very specific definition of what component means. And I tried to make a rigorous definition and say elements or components. And then initially I used elements, and people would come to me at a conference and say, why do you call it an element? It's a component. Okay, I call it a component. So
that's it. So my question here, if you would use some formal architectural language, would that force you to make more like
Yes.
clean?
Absolutely, it would. And one of the things that we would like to do is formalize this architecture using a language, maybe HTML, which is popular in
Yeah,
our research group. And then there you don't have as much ambiguity. That is something we would definitely like to do. The reason why we didn't do it, and no offense to Chen who is here, is that there was a choice. You could either build the prototype or you could sit in front of a computer and model it in the tool.
It's your thesis, you should not blame others.
Yeah. So we chose to actually build the vehicle rather than sit and model that.
It's okay, it's just a reason. Okay, I think I'm approaching to the end. Okay, so I think we went to many questions. I'm pleased with your answers, so you were able to answer in a good way. So by this point, thank you from my side.
Thank you.
Yeah.
Thank you very much. For a nice discussion here. So we now move forward to the next part here, which is the open questions. And then we first turn to the evaluation committee. So I would like you to ask the questions you may have to the respondent. Would like to start? Please. Oh, the microphone. Yes, that's a good idea. Actually, it's a very good idea.
Okay, yes, it's on. So, a few complementary questions to what you've already heard. You said in the introduction that your main contribution, as I understood it, was two reference architectures, one for cooperative driving and one for autonomous and automated driving. So, I had a few questions how these differ from each other. One was concerned with the supervisor that we talked about a while ago, which is very prominent in the cooperative driving case. But I cannot see that in the autonomous driving architecture. Can you
Yes,
that?
absolutely. The supervisor was one element and an important element in the cooperative driving architecture. What we realized when we went beyond cooperative driving is that largely the role of the supervisor when it comes to how to operate the vehicle is taken over by the entire cognitive driving intelligence. So you could say that that particular aspect of the supervisor's functionality has moved to the cognitive driving intelligence. And there is a second aspect to the supervisor's functionality, which is that of doing things like monitoring the health of different components, and that you do not see at all in the architecture on automated driving. And the reason for that is we realized that having one supervisory component for the entire architecture probably would not work. If you look in terms of functional safety, you actually need to look at the requirements of each architectural element and decide, does it need to be redundant? Does it need just to be monitored? Or does it need to have a supervisor? And one of the ongoing researchers is, how do you decide which architectural element needs what kind of supervision? And then can you have a number of different supervisors sprinkled across the architecture? And then can you go one step further? And can you link all these different supervisors to have a supervisory network in the architecture? So the concept of one supervisor component in the cooperative driving architecture essentially transformed into a full-blown supervisory network in the autonomous driving architecture. And this was considered to be something that realizes extra functional properties like safety, and then it went out of scope.
So it sounds to me that your understanding of this supervisory role has increased quite a lot between these two architectures.
Absolutely, and we realized that a rather simple component encapsulating that functionality won't really work it would still work for cooperative driving because it's still a very narrow and limited area. But when it comes to full-blown autonomy, you have to consider things like, what if my HVAC system is consuming too much electricity? What does that mean to my path planning? When you have that kind of interrelations, having one component just doesn't work.
Another question which you touched upon right now was also in the cognitive part here. Planning is usually considered quite an important element, but it's not very visible in your architectures. So where is the planning element in this one, for instance?
It's part of the decision and control element. It's under trajectory. The thing is, a planner creates a plan, and the plan is strictly spatial if you are being rigorous about usage of the words, and then you attach time to the spatial plan and you get a trajectory. So you generate not just one trajectory in autonomous driving. Typically you generate many different candidate trajectories, then you choose one trajectory, and what really goes down along this arrow, at least for our particular implementation, is a set of trajectories. There is one trajectory that takes you from where you are to your destination, and there is something that we call an emergency trajectory. So that if your entire sensor stack and cognitive driving intelligence just blinks out, can you still follow an open loop trajectory in the hope of coming to a safer situation? And if you have such a trajectory, and if you can show that the vehicle platform can relatively blindly follow such a trajectory, the safety analysis on the requirements in your cognitive driving intelligence drop down. Otherwise, you have to make sure it's never going to go there.
You talked a little bit about this planning problem at the end of the questioning before, and you said that there's this issue with the non-determinism and the time for executing a plan. And if you make, again, the parallel with the human driver, the human driver does also not have unlimited computational ability. So what would a human driver do in a situation that is so complex that it's harder to find the plan within a sufficiently short time? What would the human driver do?
Yeah, great question. What a human driver does is actually simplify the problem drastically. What a human driver first wants to do is not collide with someone. And that is something that humans can process very quickly from their visual cortex compared to pattern recognition, where you actually need to consider things pixel by pixel or through a moving window of pixels. So one, I would argue that there's a multi-part answer to your question. One, I would argue that humans are far superior to any computer today when it comes to processing information from the visual cortex and acting upon it. And the second thing is, humans don't always take the perfect decisions. And to just go into a slight tangent, this question has been asked to me many, many times by people asking how autonomous driving solutions solve the ethical dilemma. If you want to kill a child versus an old person, how would they choose? And we can get into that because I have a list of answers for that ethical dilemma. But the answer really is humans cannot take those decisions either. I have been driving for 20 years. I've never had to take that, which is not really a good argument. But the point is, what most humans do in such a situation is they slam on their brakes and they hope for the best. And cars can do that too.
Yeah, exactly. So that was, they usually slow down at least, or they try to increase the distance to different obstacles. And what they do by that is basically that they extend the available time for making decisions. Yeah. So did you incorporate that kind of functionality in your implementations, that you actually dynamically adjust the set speed of the vehicle to? We
didn't have it in our autonomous driving implementation, simply because those algorithms are a bit complex. We did have something similar for the cooperative driving situation, because what you do in the cooperative driving is you're actually getting information not just from the vehicle ahead, but the vehicles ahead of it. So, for example, if you see that the vehicle ahead is slowing down, as a human, you would start pressing the brake. But if you know over the wireless that every single vehicle ahead of the vehicle is actually accelerating away, and the gap between those vehicles is increasing, you are maybe not as keen on pressing the brake, because you say most likely the vehicle ahead is going to accelerate. So you do have some kind of bigger window for decision making in the cooperative driving case. You can have it in the autonomous case. We didn't have it.
Okay. So these two contributions, these two architectures, wouldn't in practice most vehicles like to be both cooperative and automated? And in that case, you think you could find a unified architecture that encompasses both?
Yes, the maximum benefit would definitely come from cooperative and automated. A unifying architecture can potentially exist. I see scope for unifying these two contributions, and there have been experiments near Palo Alto done by the University of Berkeley for that. There's a number of technological problems though that need to be solved in order for that to happen, namely that wireless communication is not very deterministic, and if you want to exert active control on your drivetrain using data that is coming in from the wireless, today's wireless technology is not really there. And if you have a human being in the loop, humans resist very hard in handing control over to a machine.
But this is what you already do in the platooning case, right?
Mm-hmm. Yeah. And in the platooning case for trucks, it is relatively easy. We've actually not succeeded in practically applying cooperative driving to passenger cars. There is only one known case that I know where, outside of an experimentation scenario, of course, where people have succeeded. And it's actually funny, they use human psychology. There is a switch on your dashboard of the car, and you can toggle it to one position where you allow an external entity to take control of your drivetrain. And if you toggle it in the other position, you don't allow them to do that. And this was in the US. If you put the switch in a position where you allow the car to take over, you have lower insurance costs. And when they did that, then drivers were like, okay, maybe then I will put the switch in that position. Otherwise, no way, I am the controller of the car. So the societal problem is a big one, and trying to address a social problem using technology, in my experience, doesn't work.
Okay, so one final, I think, question. You talked a little bit about related work, and you said you haven't found any related work on reference architecture for these kind of problems.
We did find a lot of related work on reference architectures, but not for autonomous driving.
So you referenced the RCS architecture.
Yes.
I assume you're aware of the 4D RCS?
Yes.
Yes.
From NIST and IST.
Yeah, so is that an example of a reference architecture for automated driving?
I've seen the implementations, and as I understand it, they don't apply it in real traffic. They use it morely for autonomous vehicles. I've seen application to space. Please correct me if I'm thinking of the wrong architecture. In aviation and space, the problem is only superficially similar to that of autonomous driving. The actual architectures are very different.
No, this is applied to vehicles.
Okay.
Yeah. Okay. I think the main difference compared to your work is that in that reference architecture, it's much more hierarchical. Now in this version, the second, the autonomous version, you actually have 3 hierarchical levels instead of 2.
Yes.
But does it make sense to add more hierarchy? I think. Or what is
What I would say is at the top level, these 3 are sufficient. But inside the cognitive, you can have more hierarchies. So you can have a hierarchy within hierarchy and make it hierarchical. But at the top level, I would argue that these 3 are sufficient. You have a teleop, you have a cognitive driving intelligence, and you have a vehicle.
Okay, I recommend you take a look at the 4D RCS.
Absolutely, thank you.
Thank you. Okay, there's been many questions on these reference architectures, of course, but I still have some on your hypothesis.
Mm-hmm.
You say that it is for highly automated,
Mm-hmm.
and this should help you to get a good solution.
Mm-hmm.
And you also say that this is especially with regard to performance and safety.
Mm-hmm.
So you have little bit ruled out safety. You said you don't want to go there, okay?
Yes.
However, it's quite important.
Yes.
This is coming up all the time.
Okay.
And I would say that safety, one part about classic fault tolerance, redundancy, fail-safe behavior, this is already there in all embedded systems with automated or whatever. And fine, you could say we have solutions, we know these things. But then another very important part, which I think is even more important for going into more automated control, is the intended function. So I work with avionics, and the most important part is intended function and fail-safe function. So safe function and intended function. So my question is, did you look into intended function? Since you are going from the intended function of a human, and we would like to have this intended function implemented in a computer instead. So this is completely new. So have you in your reference architecture anything that is kind of addressing the intended function in terms of autonomy?
Yes, but not to the level of rigor that you would expect if you are following a standard from avionics, where you talk about intended functions, or even ISO 26262, where you have, I think they call it a safety item or safety element. We had rather simple heuristical rules for what kind of behavior we expected, and these were not formalized. We made a few hazard analysis, so we had safety goals, but we didn't have intended functions.
About this hazard analysis, I saw in you list some the developing assessment for the future safety assessment, and you said that we needed better to understand new tools and assessment because the ones today they anticipate.
Can you just tell me where so that we can anchor the discussion?
Let me see. They depend on the availability of a human to take control. This is our future work, the first one. And you say that one way to advance is to have more tools for safety analysis and assurance. Well, I think that the ones available do not depend on the availability of a human, but there is a human because we cannot mitigate the risk. We are not knowledgeable enough to exchange the person to the machine. It is not run on the assessment methods. It is just our understanding of the situation awareness. So this, I would say, is the main challenge. And of course, there is always good to have good analysis tools, and they are maybe very manual, but they do not depend on decisions from humans. So this is kind of where we end up. We couldn't go there, so we have to have the procedure to mitigate.
Right.
Yeah.
I would like to explain a little bit the context behind that statement.
Yeah.
And if you look at vehicles today that have a human operator, and then if you look at the hazard analysis conducted on things like brakes, for example, many of the hazard analysis chains end up with the human operator taking control of the vehicle. So if you look at a hazard analysis done by Scania or by Volvo, you will find many instances that the mitigation situation is the human takes over and brings the vehicle to a safe stop potentially. But what if you don't have a human in the cabin? Then you would need to do a very different kind of hazard analysis, because you can't stop your analysis at human being takes over. And so the idea is that we need better methods of analyzing our hazards so that we can go beyond stating that, okay, the solution or the mitigation measure for this is human taking over.
Well, you need a better way to mitigate the hazard.
Yes.
A different way. Yes.
Yes, absolutely.
Okay. And then I would like to, you can look at these pictures you have up here, and I would like you to elaborate a little bit about what you have validated You say you have done a reference architecture, and it's true that it is validated. To me, validated, then you have the correct and complete sets of requirements for whatever the system is going to do. So here you have several prototypes. And you have applied it for different applications, so to speak, or implementations. So, but the validation part, if you go to, I think it's above or below this picture, you have the features of autonomous driving function, the components. It's figure 3 in paper D in your thesis. Oh yeah, this one.
Okay.
So could you say something about the validation? Have you done any validation of requirements for decision control or perception or the platform? I would say that it's not really specific to autonomous driving, so that it's fine if you didn't. But for the other ones, I would like to know what characteristics or requirements is validated.
Absolutely.
Yeah.
So first off, delimitation. We've not validated algorithms. We've validated architectural elements. So in our prototypes, we had a decision and control element, and it was running some kind of algorithm. And what we saw, for example, was from an architectural perspective, does it have all the information that it needs? Can it finish executing in the time that it requires? If the decision and control component goes down, can the architecture detect it? Can it start up a different decision planning component in case the first one goes down? Can we have diagnostics which enable us to determine the health of the component? Those kind of validations we've done. What we've not done is validate that we have an algorithm that definitively finds a path among obstacles. So we've tried to separate the algorithmic issues from the architectural issues.
But have you advanced in automated driving? If you do not look into the program of automated driving, in the sense the validating that you actually have the correct algorithm, I mean, if you have a small set and you have assumptions, and of course you always have to have this to learn and to understand. But you validate that, okay, for this example,
Absolutely.
it's functional. But
Yes. So we have been validating the algorithms, and now I'm saying we, not me, because I don't want to claim that I did the validation. So this research validated the architectural assumptions. The algorithms themselves are definitely being validated. So when we talked about the implementation, here we are talking about virtual sensors in a synthetic 3D environment. So we've been building up databases of things where a person suddenly jumps in front of the car, or the distance to the curb changes, or we change the friction of the road surface. And every time we make a small improvement to the planning algorithm, we put it on a virtual car and we drive it. At the moment, we have somewhere around 10,000 different test cases. And we drive the car using that algorithm through every single of those test cases. And then we have metrics. How close did you come to the pedestrian? How much time did it take you to react? And then we look at all the metrics and say, only if we see a clear improvement is this planning algorithm going to work. There is a set of test cases. If they fail, it doesn't matter how well it did perform. In the other cases, this is not going to work. It's not validated. So we've been doing such validation, and that is very much a core part of autonomous driving. I just don't want to claim that I'm the one who has done that as part of this research. Yeah. But for autonomous driving in general, sure, absolutely.
okay, I think I am happy with that answer so far. Thank you.
Dear Sagar, I would like to start with complimenting you with the work you have done, the thesis. I've been reading it with great pleasure, and what you see is that while reading, all the time questions pop up because you introduce many concepts, etc. So you question how will he do this and how will that be related, etc. And then a few pages later, typically you address the question and sometimes you even answer the question. So I think that is a great achievement to have a full thesis where that many questions are raised and where many of them are addressed and even some of them are answered. So congratulations with that aspect. Now to some questions. First of all, I would like you to go to paper C and then page 1102. And then especially there is at the end of section 3.3.5 control.
Okay.
And if you can read the last sentence of 3.3.5, starting with beyond these arguments. Please read that out loud.
Okay, so the sentence that Garrett is referring to is, I made a bunch of arguments and then I say, beyond these arguments, the actual classification of the control element is of importance only to compulsive categorizers and adds no value to the architectural description.
Yes, and this sentence brings me into great difficulties.
Okay.
The problem is I'm teaching many students how to write academic papers.
Okay.
And now I have to revisit how I teach them in two aspects. Well, one aspect is I'm telling them academics don't have a sense of humor. You violate that one in this sentence. And the next aspect is I teach them that for every statement they make, they have to give an argument or evidence, etc. And that's the other one you violate, I'm afraid. So I would like to ask you, can you briefly explain this sentence somewhat more, elaborate on it? Why did you write it the way you did write it?
Okay. I'll answer your questions in sequence. My first draft of any paper I write typically has a lot of informal language because I hate it when papers I read are dry and boring. Some of the best texts I've read have a lot of humor, it just makes it fun to read. Typically, as it goes through reviews, we start removing the fun parts, I think. But occasionally I succeed in sneaking in sentences like this. So if it can't be a good example, let it at least be a terrible one. Now, coming back to your second question. What we have in this architecture, right. So what we say is, you have your model data, and then you have your model data consumers, and then you have a separate control block. And this control function is actually connected to the world model through a bidirectional arrow, not through a unidirectional arrow, so that different internal variables of the control function, things that the control function is going to do in advance, can all be reported back to the world model, from which they can be pulled out to different consumers. Now, the word consume means to take the data and to use it. The control is taking the data and using it. So you could argue that the control is also another consumer. Sure, but it is much more than a passive consumer. Compare it with the HMI. The HMI typically displays data. It's a one-way read-only kind of thing. Whereas the control is pumping a lot of data back into the world model, which can then be used to the HMI. So I wanted to highlight the fact that the control is not just another passive consumer, it's much more than that. Now, beyond that, if people want to say, no, but it consumes, so it's a consumer, fine, then you are a compulsive categorizer, I don't care. Okay, I shouldn't say it that way, but so the point is, it's much more than just a passive consumer. So it's worth pointing out that it is different.
Thank you. I think this is a good diagram to keep on the screen. a lot of discussion has been on this reference architecture and what is it and what is it not. And of course, the question immediately also relates then, and what is then architecture? The way I define architecture is richer than most people use it. Many people use it for something that I would call structure. It is the structure of the elements and how they are connected. That's what people often call the architecture. But I think an essential element of architecture is the way things fit in the context. So if you create an architecture, you not only create an architecture of the thing you're making, your autonomous vehicle, but also of the context of the autonomous vehicle and your understanding of it. And I would assert that an essential part of reference architecture is that you capture the inherent knowledge and understanding that you have of that domain. And simply, if you go to any companies, there are those people that have been working there for a decade or a few decades, and they have it all in their guts. They know how things relate and why certain solutions fit certain contexts. And if you do nothing, then that knowledge stays in their guts. And it's very difficult to instantiate next architecture because going from guts to instantiation is really a challenge. So now if I look at this diagram, one thing that I have a little bit difficulty about is it is very egocentric. It is very much focused on the vehicle. And the way I would look at the architecture, this world model, I think there is a lot of knowledge, and you have shown a lot of knowledge in the past 2 hours about the domain. And I think that it's specific world model knowledge, but it's not world model knowledge, it's fact context knowledge. Can you tell us a little bit, do you have anything deeper than this diagram on the world model or the contextual knowledge that you all the time are using and which in fact is part of your reference architecture?
Yes, I can talk about it. First things, coming to what an architecture means, I completely agree with you that the term architecture needs to have a richer meaning, and in fact you made a white paper called The Role of Chief Architect, and I read that, and that was the first time I thought somebody who gets it. So that's a good thing. Now, coming to the context. Yes, contexts are important for architecting. In fact, if you look at the formal definition of architecture, it talks about representation of elements in context. Now, there is something, at some point you draw a boundary around something and you say, this is my system. And then you can have a system of systems. And that what is to you a system of systems, to somebody else can be a system. So in paper C, what I do is, I explicitly state somewhere that the scope of this architecture is delimited to that of the ego vehicle only. So the world model here has more information on the ego system state and whatever minimum necessary information about the other actors, which are the other cars and so on. What I've not done in this paper is claim that we have the context of the system of systems which makes a platoon. So if I were to talk about cooperative driving in general, I would definitely focus on a system of systems. But what I've talked about is a reference architecture for one vehicle that is part of a cooperative driving scenario, and the architecture is delimited to that vehicle only. Now, going out of what has been published, we can discuss a lot about the cooperative driving, but if we are going to ground it in this diagram, then I would say system of systems, no, it only talks about one system. Does that answer your question? I'm happy to talk about cooperative driving, but I'm reluctant to give the impression that cooperative driving is addressed by this architecture.
I think we need to go after to discuss that, so I'm satisfied with this answer.
Okay.
I think another point that popped up in the previous questions were the extra functional requirements and properties. And similar to what I said before, I think in a reference architecture, it's you try to capture the inherent knowledge, and inherent knowledge is functional, and you said well, the function is heavily overloaded, so what it means is not that clear. But I think that very essential are these extra functional properties. And safety has been mentioned many times, but I think in this case, driving experience, driving comfort, all those kinds are extra functional properties that are very important and necessary to think about. And then timing popped up in one of those questions. And I would assert that the conceptual aspect of timing ought to be part of a good reference architecture. And for example, also discussed a few times is in these kind of architectures, the system has historic knowledge and has anticipated knowledge, and what you see is there are many time horizons. You can look a little bit ahead, and you can look a bit further ahead, and you may look even further ahead. Can you explain a little bit what time horizons, in your opinion, play a role in this reference architecture?
Yes. I would say that different elements of the reference architecture will have different time horizons. So a path planner, for example, can have, if you're driving from here to Gothenburg, your planner might at the highest level have a time horizon that spans 5 hours. But in the lower level control loop, you could actually have a time horizon that boils down to a few milliseconds. And Jakob mentioned the NIST architecture, and they capture it pretty beautifully because you have a set of hierarchies. Imagine like a big triangle. At the top, you have the big element, and then at the bottom, you have many elements. And as you go from top to bottom, the timing horizons reduce, and as you go from bottom to top, the abstraction level increases. That is unfortunately not well captured in this architecture, and I've really admitted. What I can say is that there will be hierarchies inside each architectural element, and what I can also definitely state is that each of these elements will not have the same time horizons.
And you also recognize that giving guidelines on what time horizons to use may be useful for instantiating those architectures.
Yes.
So that should be part of a reference architecture. Yes. I think we have shaken you enough, so I give the word to the chairman.
Thank you very much. Thank you all in the evaluation committee for a good discussion here. So now it's time to see if there are any remaining questions from the audience. Yes, we have discussed for a while, but please don't hesitate. Yes, down there. Could we? So we have someone passing down the microphone.
I have a lot of questions, but I will limit it to one. So I think you're in a unique position to make some prediction of the future. Could you say something about what you think we will see, like 5, 10, 20 years?
Oh, okay. What I can say is that in the near time horizons, autonomous driving is expected to really emerge by 2019 or 2020. That is the time horizon that is repeatedly discussed by all the big automotive companies in the autonomous driving conferences. What I will also say is autonomous driving is not really an all or nothing proposition. So there's different levels of autonomous driving, as we saw, and we will of course not have full autonomy in every possible scenario in 2020. We might not even have it 20 years down the line. So I can tell you a little bit about how this will roll out. An important concept is known as geofencing. So you will only allow autonomous vehicles to operate within certain geographical locations. And one of the things that will be required by law, this is happening, is you as a vehicle manufacturer need to tell the government authority under what set of circumstances, geofencing, environmental conditions, and so on, atmospheric conditions, precipitation, snow, you need to say under what conditions will your car perform. Then you need to demonstrate two things. One, you need to show that you can back up the claim so that in those conditions your vehicle actually performs. And two, your vehicle has the ability to show when it is going out of the envelope, so to speak. And then it needs the ability to come to a safer state when it is going out of the envelope. So in 2020, limited mobility, no more than 25 miles per hour, that is the sweet spot for a variety of reasons. That is where you will have autonomous driving, especially in urban cities. Then you have the highway pilots, which is more or less already there, but it still can't handle things like traffic lights and so on. And then you have different sensor sets. So the only prediction I would feel reasonably confident of making is better autonomy up to 25 miles per hour in geofenced areas in big cities. This is something I would feel comfortable making, and they say that the best way to predict the future is to invent it. So to put my money where my mouth is, I'm actually a part of a company who has a business plan of introducing products in 2020. So that is why I feel confident of making this claim. Whether it will work or not remains to be seen.
Any further questions? Yes, please.
Could you go to slide 31, please, where you have the architecture for GCDs, I believe it was.
Slide 31. Yes?
In the beginning, during your introduction, you mentioned that looking at the autonomous or cooperative functionality of the vehicle as a monolithic entity that gets added on top of an existing architecture was a simplistic way to view it, and that you believe that code design of the entire architecture would be required. However, in this picture, it does seem like the autonomous or cooperative functionality is added onto already existing architecture here.
Yes.
And I believe that you also mentioned that you performed fairly well in this GCDC competition.
Yes.
Could you elaborate on what makes you draw the conclusion that this might not be sufficient?
Absolutely. So the context for this is this was cooperative, not autonomous, and this was a vehicle that had a human safety driver ready to take over in case something was going wrong. The final vision was also to have a human safety driver in case something goes wrong. So when you have those guarantees, then it is definitely possible to just put something on the top that eases the load on the human driver, and you know the human is ready to take over. So for cooperative driving, just adding something on top totally works. For autonomous driving, especially that kind where you cannot guarantee that the human will take over, this will not work. Then you need to have really tight interaction, and then just adding something on top is not an option.
All right, thank you.
Yeah.
More questions? Yes, please.
I have a question about the fiction application C. As you were also involved in some of the evaluation platforms, I assume.
So which platforms?
The evaluation platform. You said that you had 4 platforms where you evaluated the architecture.
Right.
You said something that you used the GPS and the NTPD for synchronization.
NTP.
Yes.
Yes.
And as we know that for the cooperation, timing is crucial.
Yes.
What was the motivation to not decide to go for the precision timing?
For the which?
Precision timing.
PTP. The other participants in the competition were not using that. So there's 2 kinds of timing synchronization that is necessary. One is in your own system, in your own vehicle. If you have a number of computers, you need to synchronize those computers, and you need to synchronize time with the other participants as well. So NNTP was good enough for synchronizing time between computers on the same network in the same vehicle, because theoretically its limit is I think 12 picoseconds, and you never need that kind of synchronization. So basically a working implementation was available. It's part of every Linux distribution. It does the job. Fine. If we didn't have an NTP protocol, what else would we have used? The most common thing to use is the PPS signal. It's a pulse that you get on a GPS receiver. Not all GPS receivers have that, so you don't really want to make it a part of your reference architecture. Only relatively expensive GPS receivers have the PPS thing, and then you need an additional wire on the GPS along which you get the pulse. So since we had NNTP and it worked, that's why we went for that. If not, we had a pretty expensive GPS, we could have used the PPS pulse. And when it comes to 10 different trucks on the road, using GPS time really is the only option. Does that answer your question? Okay.
You. Anyone else has a question? Yes.
Nice.
You mentioned somewhere in the book machine consciousness.
Right. Thank you.
Do you think machine consciousness will have any essential impact on architecture?
Yes, it will, for sure. The question is along which time frame. So Patrick here has been working a little bit on something, I don't know if you call it consciousness, but at least approaching consciousness. And there have been architectures that talk about machine consciousness. And the impact it will have, as I see it, is you won't have to sit and think about all the things that can go wrong in an architecture and make provisions for it. So what you would expect is if the machine is capable of introspection, if it knows that I have these 3-5 different parts and this is the function of each part and this is how the parts work together to solve the problem, then the conscious machine can reason better about how those parts should work together when one of the parts goes wrong. A concrete example, one of the popular architectures in avionics is IMA, Integrated Modular Avionics. And the next version of Integrated Modular Avionics is actually looking at if one of the ECUs goes down, can we migrate functionality from this ECU to another ECU so that you can keep functioning? This will happen when the passengers are getting loaded and unloaded, not in the air. But then, since there is no consciousness as such in the machine, we need to sit and handcraft and say, which are all the different permutations and combinations of functionality and the ECUs on which they operate. And then you make a formal model, and then you run it through a massive model checker to show that for any possible allowable combinations of mapping of functionality to the ECU, the system will still meet certain properties. And this is a large exercise. The state space of these systems goes on exploding. If you had a conscious machine and you could guarantee that it is basically going to do its best to make sure not to screw up, I foresee definitely a time in the distant future when we can leave that decision making to the machine. Because today you as a human, you don't go through every possible step you will take to ensure that your car is safe. But every other driver on the road trusts that you are a conscious, self-aware, reasoning human being, you are going to keep the car safe.
One more question over? Yes.
I have one question about modularity.
Mm-hmm.
Does your functional architecture is possible to slice according to some modularity, support modularity, or scalability?
It can. You can't slice this architecture itself, but what you can do is when you start implementing the functional architecture down at the technical level or the software level, you can assign the functionality of different blocks or different elements of the reference architecture to different modules. So at this layer, the modularity is really at vehicle platform, cognitive driving intelligence. And within that, you have some functions like localization and so on. But inside your vehicle platform, let's say that you have a ABS controller or an electronic stability controller. Can you allocate those functions to different ECUs, to different tasks? There is a lot of scope for modularity there at the implementation level. At the reference level, not so much. Mm-hmm.
Yes. My name is Matsus. I work with service design. Question: why did you choose to join a startup instead of the 100 big players?
Great question. How often do you get a chance to start with a clean sheet with very little constraints, financially, technically, in the big companies? If I go to Volvo or Scania and I say, guys, your ECUs are running 400 megahertz. What is this? A microwave? Throw it away. Get gigabit, get fiber. This is this amazing GPU with 4096 cores. Get it all now. Let's prototype with that. Been there, doesn't always work. If I say you have what 80 ECUs, this is insane. Collapse all the functionality into one really big powerful ECU and replicate it. Do you think Volvo would allow me to do that right away? Probably not. But when I'm at a startup, I call the shots. there is a responsibility. You know, if it messes up, I've messed up. But that's a risk you're willing to take, because you look at the technology landscape, and in the big players, it is, I would say, at least 5 years, and that's being very optimistic, behind the state of the art. When you go to a startup, every single day I can bring a new issue. I can go to NVIDIA and say, hey, we are a startup, give me your drive PX. And before that is actually launched, we get it. So that is one reason. And the other is, it's just a lot more exciting to work in startup. Yeah.
Yes, please.
So a follow-up to that, do you think the big players would survive?
I'm sure they will. There is something called too big to fail. Well, not always, maybe. History has shown that some big players who don't adapt do fail. But if you look at, so the big players, you know, they are really learning that there are areas where they don't have enough technical chops or direction, and they need to team up with partners, and this is happening. Google, for example, who is a big player, recently announced that they're teaming up with Ford. So Ford will get access to a lot of the self-driving technology that Google has developed. There is Uber, which is trying to build their own self-driving vehicles, and a competitor to Uber is Lyft, and Lyft is partnering with General Motors. So the big players are cooperating with the smaller, nimbler players. There are other instances where you have a startup that's developing a cool technology, and a big company comes and just buys the entire startup team and all and assimilates them. So, I mean, the big players have been around for a long time. If someone has been around for 90 years, 100 years, they definitely have an eye on the market trends, and I don't think there is a risk that the big players will disappear like this. They will adapt. And the other thing where the big players definitely have a lot of clout is lobbying and talking to governments. If you as a startup go to the government and say, I have this totally cool idea, you should do what I say. And instead, if you know someone like Volvo or Scania goes and says, look, we set the standards, this is how you should do it. Who do you think will the governments listen to? So yeah, big players will be around for some time.
Yes, please.
You talked about software updates and data logging. You mentioned Google. And I wonder about your opinion about specialized tools.
Yes, so I can tell you a little about what Tesla is doing. The Tesla cars constantly talk to the back house, so to speak. And if you look at the way they implemented their adaptive cruise control, they already had all the sensors, they had the compute inside the vehicle, and they had the software functionality inside the vehicle. It just wasn't switched on. The algorithms were running. Every time the adaptive cruise controller or the autonomous emergency brake function would have triggered a brake, that event is captured together with all the other data and sent to the back house. So this then goes into a deep learning network, and you have massive amounts of data, because every single Tesla out there, every single kilometer that it is driving, all this data is being gathered. The only thing is missing is actually triggering the actuator to take action. And this data is gathered and analyzed, and maybe you realize there are areas where your algorithm doesn't perform as well. You update the algorithm, you push it back to the car, the customer is still not aware what is going on. And then when you realize that all your data is telling you, okay, I've driven 3 million miles, I have sufficiently less false positives, now it's good. You send another update that basically flips a software switch, and tada, you now have AAV functionality. So what is really crucial is before you can update, you need to find ways to test, verify, and validate. And if you can't do that, you can't update. And most cars out there don't talk back home to do this testing. So unless we see a massive change in the way we verify and validate our functionality, live updates won't come.
Yes, please.
Now you're talking about continuous experimentation. How is this supported with your work, for example?
The way it is supported is this way. If you look at the implementation setup, whenever you get data from the drivetrain, you can actually simulate all of it in a completely virtual environment. So continuous deployment. If you come to me tomorrow and say, I have a better algorithm, normally I would have to put it on a car, drive it around in the real world for 3 million kilometers, and then say, okay, this looks good, or maybe this looks bad. What I can do in this is I can put it in the virtual environment, I can run it on a supercomputing cluster. In 15 hours, it has gone through 3 million kilometers, and it's giving me metrics, is it good or bad? If it is good, I'll push out an update. So that way I get continuous deployment. Ties back to what we said about verification and backend infrastructure. If you don't have ways to quickly validate any changes, they are not going to get pushed out. The architecture supports it by means of implementation setups.
I was not referring to continuous deployment,
Okay.
continuous experimentation.
Continuous experimentation.
So that you actually deploy software into the fleet of cars,
Mhm.
like real data, not just virtual data.
Okay.
So how is this supported?
This thing doesn't have that. Yeah. Mhm. Mhm. Absolutely. It is the number one thing because we have a lot of high profile investors and we already have 3 vehicles driving around in which we give demos. And if a man is worth $1.3 billion and we are putting them in our vehicles, we really don't want to kill them. So we are looking at safety all the time. And architecting is often left behind, but safety comes first. And the thing is also, it's not just a responsibility of killing one person or not. If you drive your car on a public street today and you have a bad incident, you have the potential of setting back entire autonomous driving by a few years, because if there is a mass uproar and protest, his self-driving car, it killed a man. That's it. So safety is very important. We will definitely look at what is done in the aviation industry. Things like triple modular redundancy are important. I don't really see it coming in cars in a big way, but definitely aviation has led the entire field.
We have a mix of automated and unautomated traffic today.
Mhm.
There are problems.
Mhm.
We also have the problem of semi-automated functions.
Mhm.
The pilots take long decisions, and you can adapt this also the car.
Yes.
So you have this HMI. Sometimes when you go to fully automated, it
Mhm.
might be in a way easier because you don't have to consider
Yes.
the person might or might not do it, might do 90%.
Yes.
So I was just interesting. So maybe I can follow you in the future.
I would love to chat with you. Aviation is definitely, I've personally analyzed about 135 air crashes to see what went wrong and sometimes if it is the human. We are definitely working with companies who supply military drones to see what we can learn from them. And it is completely true that this level 3 partial automation is actually partial automation is a big problem. And in 2014 at the Autonomous Driving Conference in Berlin, the entire focus was on How do you inform the human to take over? What do you do if the human doesn't take over? What are the studies? If the human is reading a book, how much is the reaction time? If the human is sleeping, how much is the reaction time? But if you go to completely automated driving, you actually leap over one of the biggest problems is human handover. And we just don't want to do it.
Also, we are also, as you said, you had 98% forecast blaming on the driver.
Mhm.
For accident, and the underlying industry, this is also happening. It's increasing the decisions from the pilot that make them not be true. It is all this interaction. But
Mhm.
that is a big problem. I would say nobody knows.
Yes.
And we need to decide to default on that for some system for what we do.
Mhm.
So we know that. Then we have unknown.
Yeah.
And I think this part, unknown, which is not reachable,
Mhm.
will increase when we go to full application. But I'm not sure. This is how I feel about it.
It will, and I would love to pick your brain about it for a very specific reason. Like, I'm a pilot myself, and my flight instructor flies the big A330, so I had a chance to go into the cockpit and observe how they do crew resource management. There's just a lot of information, and I imagine in a fighter aircraft like the Gripen, there's even more information, and you have only one pilot. So this pilot is responsible for flying the aircraft, doing all kinds of tactics, and engaging. And there is only one pilot. So I would love to learn what kind of information you present and how you filter the information you present to the human to make sure that this doesn't, something catastrophic doesn't happen.
In the interest of time, I think we are actually running late here. So if there is any question left that actually is really related to scrutinize the work and not mere speculation or discussion because it's a lot of fun, I would invite that. We have one more question. Okay.
Okay.
Need your hands on.
Yes.
Can you just tell us about is your architecture realizable? Can it be realized?
It's realizable using AutoSAR. I wouldn't recommend it. I'm not a fan of AutoSAR, but I know it's what the company is moving towards. AutoSAR, as I understand it, is very much at the implementation level. It does impose some restrictions on what you can achieve in the technical architecture.
But also the methodology part.
Mhm.
I would like to get your view on that.
Okay.
Because it has been a huge investment.
Yes.
And is that basic if you go to driving, or do you have to do another big investment to this?
I don't think you'll have to make another big investment. The methodology for AutoSAR that I've seen, I'm not a big expert, should be applicable when you instantiate a reference architecture like this. Where I see AutoSAR's bigger limitations are the fact that the technical capabilities that it provides, you might need a lot more than that for autonomous driving in order to create better architectures, more relevant architectures. Example, please correct me if I'm wrong, AutoSAR does not support publish subscribe. It's mostly client server communication. And in AutoSAR, you need to specify in advance every single communication between the components, and this has to be statically presented. In some of our architectures, we are like, there is a pipe between this component and that component, and it's tossing a black box, and unless the receiver actually sees what it gets, it doesn't know what has come on that pipe.